Okay. So we are in the middle of gaining some intuition on PAC learning, and our objective is to, once we complete that, we're going to see how it's used in boosting. Now, one of the things I mentioned last time that for a finite hypothesis set, ERM gives you the right enables learning. ERM, it simply means that we choose out of the set, the hypothesis set, we choose the hypothesis that minimize the loss on the training set. Okay, so let me take another example so that we better understand the PAC learning concept. So if we look at the PAC learning concept here, again, you see that the definition says that for any epsilon and delta, epsilon being how much we're going to make a mistake when we deploy the model. Okay, look at this formula. This is how much we're going to make a mistake on the average. And this average is taking on the model once it's trained, and it needs to be less than epsilon plus this correcting factor. The correcting factor is basically to handle the case where the optimal or the hypothesis that we're trying to learn is not in the hypothesis. So we can't be expected to do better than the best hypothesis in the hypothesis. Okay, so that's the epsilon, and the delta is the chance that we're going to sample enough points, but still we're going to be unlucky and not being able to learn. Now note that you can think about the PAC learning definition as a game. Okay, so there's some player that is choosing the probability, and then the learning algorithm reacts in picking up enough points and doing something to get the objective. So it's like a game in which the adversary may choose the probability that is makes the learning as hard as possible to the learner. Okay. So let's look at an example. So assume I want to think in terms of so x is going to be just the real numbers, okay? And with respect to the probability, our adversary likes Gaussian. So I'm telling you a secret, okay? So the adversary chooses out of two Gaussians that we don't know. In probability, half the first Gaussian is chosen, okay? And in probability half, the second Gaussian is chosen. And then the adversary chooses a point using the Gaussian. So say the adversary flips a coin and chooses this Gaussian. And now using this Gaussian, Gaussian number 1, a point is chosen here. Okay, there's some probability of getting that point. We choose a point here. And now we label it as minus. If we're using the second Gaussian, then maybe we flip the coin and we choose the second Gaussian. Again, and then we choose a point here, maybe. And then we label it as plus. So this is the process of the adversary. Now, usually we don't know that. I mean, we don't know what the adversary is doing, but I'm telling you the secret. So I'm telling you what the adversary is doing. Now, can anyone tell me what would be the optimal classifier here, given that you know what the adversary is doing?
Is it to like basically take like the lowest point of the intersection of the densities and then just simply give it like -1 if it's on one side and plus if it's on the other?
Yes,
like
so
that?
that's the base. That's basically the base rule. So Sam says correctly that say I'm giving this. I want to classify this point. So I'm looking at the density. The density here is lower. This density is higher. Then according to the base rule, which we can prove is the optimal classifier, we're going to give this point a plus. Right? And the same thing for any point. So if we know the two densities, then the base rule will tell us exactly what to do, and that's the optimal classifier. Now, so I'm going to choose a hypothesis set that is going to be a threshold, a threshold in R, and if X is bigger than T, then I'm going to say plus, and if X is less than T, I'm going to say minus. Okay? So that's a hypothesis set, right? Is it finite or infinite? So is the hypothesis set finite or infinite? Anyone?
I'd say infinite.
Yeah, it's infinite. It's infinite because it's basically, you know, it's any number, right? All the threshold in R, so it's basically equals to R. Okay? So it's infinite. Now,
Eitan.
yes.
Sorry, so just to clarify, when you're asking if the hypothesis set is infinite or finite, you're saying the number of possible hypotheses we could want to test. Is that infinite or finite?
Exactly.
Okay, because there's an infinite number of thresholds you could.
Yes. Yes.
Okay, got it.
exactly. It's very important to get these abstractions. Otherwise, the definition here doesn't mean anything. So when I'm saying, if you're looking at this H here, then when I'm saying it's finite, then I would mean that I'm only using a finite numbers of thresholds. Okay. So instead of T, a member of R, any T, then I will have T1 to Tk. That's it. I can't. I have a finite hypothesis. Okay. Now, so Sam said to take the higher density. Is there a threshold here you can pick that will give you the same result?
I don't think so, because the densities overlap, right?
Yes, but for each point, I'm coming and I'm picking up the bigger.
So, oh yeah, so it's the threshold where they intersect.
Exactly. So this one is a threshold that gives us the optimal base rule, right? So we have the optimal base rule in the hypothesis set. Okay. Now what I wanted to explain is what's going to be the ERM here. Because I'm saying ERM on a finite set, mind you, and will give you the optimal learning. And also when the VC dimension is finite, which I didn't explain yet what is a VC dimension. And if I explain it, then you need to determine if H has a finite VC dimension or not. You can take it as an exercise if you like. Go ahead, go to Wikipedia or to the other understanding machine learning book, by Shai Ben David and Shai Shalev Schwartz, and see what a VC dimension is, and try to prove if this hypothesis set here it has a finite VC dimension or not. If it has a finite VC dimension, then the ERM rule will give us will enable learning at an epsilon delta level for any a probability, and so it's useful to try and also understand what's an ERM. Okay, so say I get some examples here. So let me create some examples. Okay, this is the data I got. I chose like a few points. I went through the process I described, and I got this data set. Okay, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 data points. Some of them are plus, some of them are minus. What it essentially means is that 9 times I chose 1 or 2 in probability half, and then I used the Gaussian to choose the point. So for instance, when I chose this one, the minus here, it means that I chose the Gaussian number 1 with probability half, and then I chose this point using the Gaussian. Okay. Now, what's the what's the ERM here? Okay. The ERM needs to pick up a threshold that will minimize the number of errors. So can you give me a possible threshold? There's more than one. But what is a possible threshold that will give us the minimum number of errors here? Where would you put a threshold? How many errors do you have if you put a threshold here? So if I put a threshold here, this is my T, how many errors do I have? If I put a threshold here, what would I say on this point? Of the points that are less than the threshold, what do I say? I say minus, right? For the points that are bigger than the threshold, I say plus. Okay? So if I put the threshold here, then for this point, what is the reply I'm going to have using my threshold?
That becomes an error, right? Because it's plus and it should be minus.
Yeah, so I'm going to say minus here. What about this one?
That's the same thing, right? To be a minus.
Yes, minus. This one is a minus. This one is a minus, but it's okay, right? Because it's actually a minus. This one is a minus. Everything is a minus here, right? All the 9 points are going to be a minus. So how many errors do I have?
9, right?
No, because this one should be a minus.
Oh, sorry. Right.
And this one should be a minus. And this one should be a minus. And this one should be a minus. But here I'm going to make a mistake, right? So how many mistakes do I have?
Looks like 5. I'm counting that right.
Yes, exactly. Now, if I put my threshold here, how many mistakes do I going to get?
Looks like only 2.
Yeah, we went down, right? Can you do something better?
Well, if you shift it over 1, then I guess we have errors on the right side that time, right? Because you have a minus where a
If I
plus would
put it
be.
here, then this one is going to be an arrow, right?
Right.
This one is going to be an arrow, and this one is going to be an arrow.
So it's still, so it's 3.
It's 3.
Yeah.
So this one is less good. Okay? If you put it here, it's still going to be 2, right?
Right, because they have 1 on each side.
Yes, exactly. So, you know, any threshold between here and here is going to give us the ERM, the minimum error on the somethings set, which is 2. Okay? Now, the interesting point is that this one contains the optimal. The optimal base classifier, and in fact, the more points we're going to get, the smaller this region is going to get. Okay? Because the more example we're going to get here, and the more representative it's going to be, we're going to kind of narrow this one. So the probability of error here is going to be smaller and smaller when we get more points. The point of the theorem here is to tell us how many points we need to get. Okay? So that's another explanation, another example of what we mean by PAC learning. And next time, hopefully, I can get to the boot. Okay. Any questions up to now?
Nope, I think I follow. That makes more sense. Thank you.
Great, great. Okay. So thank you very much for joining today, and we'll continue next time.
Sounds good. Thanks, Eitan.
Bye-bye.